Hey everybody, Mrs. Bodechon here, and we are going to go over our AKS portfolio for 9E. It says, I can develop and use models to explain the changes in sound waves associated with the Doppler effect. So the very first thing that you have to know is, what is the Doppler effect? So let me show you this and you will see. Okay, so here's the definition of Doppler effect. It's an increase or decrease in the frequency of sound, light, or other waves as the source of the observer moves towards or away from each other. So this definition is kind of hard to understand. I'm going to show you a simulation that you can start to see the definition kind of come to life. Okay, so in this simulation, we have two dots. All right, one is representing the object that is producing a sound wave in this case, okay? And the other one is the observer. So let's push play and see. So the black one is producing a sound and it's coming towards the red dot, which is the observer. Now we're going to play this again because I want you to notice the wavelength and how it changes from when it's approaching the red dot to when it is behind the red dot, okay? So let's go back and replay this. Notice, let's go back to number 3. Okay, notice that as my dot is moving towards it, my wavelengths are really close together, okay? And then as soon as it goes past it, my wavelengths are very far apart. See how long those wavelengths are compared to right in front of this object that is producing this sound? That is because of the Doppler effect. So when you are in this portion of the waves, and I have short wavelengths, you are going to hear a really high-pitched noise, okay? It's very squeaky, and it's very, very high-pitched. Surely you guys have heard something high-pitched and squealy before, and you're like, ah, okay? Whereas if you have something like in this section of the sound waves, where you have a longer wavelength, that is going to be a very low pitch that you're hearing. So it's going to be a much deeper sound. It's not going to be squeaky at this point. It doesn't mean that it's loud or quiet. It just is based on the pitch, okay? So over here it's going to be a high pitch, and over here it's going to be a low pitch. One of the classic examples of this is a train. So say you're stopped at a train track and you're waiting for the train to pass by so that you can drive across the street, right? You hear the train coming, and as it's coming, it's getting louder and louder pitch, right? And then it's like right next to you, and it's like, whoa, this is overwhelming. But as soon as it passes you, all of a sudden, it's low pitch now. It doesn't hurt your ears as much because you've broken through all of those close wavelengths, and now you're on the side that has the wavelengths that are very stretched apart. So that's really what's happening there. I want to show you another simulation right here. That's going to go and show you the same thing, but back and forth, okay? So now we have our object making sound going towards the observer. It's high pitched for the observer, but it's turning and it's going the opposite way. And you can see where it's stretched out, that's low pitch, right? And it's going to stretch out and become even more low pitch as the object that's producing sound gets farther and farther away. And then we have our last one, and this one is just simulating it moving and kind of trailing the sound behind it, but that's even further in depth. I just wanted to show you that the Doppler effect reaches farther beyond just the basics, okay? So let's go back to our worksheet. Okay, so you have this on your worksheet for you to do. It says, describe what the Doppler effect is in your own words using real-world example of it, and you can use the ones we just used. You can put in place people, you can put in place cars, whatever you want to put in place of it to make it a real-life example. You can even use a train example, that's fine. Draw a model on the Doppler effect using an ambulance with a siren on and two observers, one in front of the ambulance and one behind the ambulance. Space the wavelengths differently based on the perceived frequencies. You also need to place an X where there is a low pitch and a Z where there is a high pitch. So here is our picture. right here of the Doppler effect. And here's our ambulance. It's moving forward, as you can see, and the siren is on. So it's producing lots of sound waves, right? Well, here's one observer, and the observer in the front is going to have a high pitch, which is why I place a Z here, high pitch frequency, because all of the wavelengths are very, very short, right? They're close together, they're short. So you can see this little image right here showing you that it's very high frequency over here, which means high pitch. But the observer behind it is going to hear a very low pitch or low frequency due to the wavelengths being stretched so far out. Okay, so this is the Doppler effect in a nutshell, you guys. If you have any questions about it, please let me know. Bye.